Have you at any point thought about what secrets are concealed in the tremendous universe? Prestigious American physicist Michio Kaku has made a revelation that vows to change everything. This revelation has been made conceivable by the amazing J. Dello. This gadget has uncovered something really progressive. Time, as we get it, doesn't exist. It is going to leave on a space-time problem that will shake your view of the world. The Webb telescope is opening insider facts from the farthest corners of the universe because of its high-level infrared innovation, turning into a definitive time machine for investigating the past. Join us on this excursion to discover how this telescope has changed regular hypotheses, redefining how we understand time as far as we might be concerned. If you're interested in staying up to date with news from the universe and its surroundings, subscribe to our channel, like this video, and turn on the notification bell. Have you ever considered how the astounding resolution and sensitivity of the Webb Space Telescope make it possible to recognize objects of extreme age and faintness, even beyond Hubble's capacity? We are referring to distant galaxies and stellar assortments of the early universe, those elusive elements that have been playing an epic cosmic game of hide and seek. In short, the James Webb Telescope is helping us in the careful reconstruction of the enormous celestial riddle of the universe, piece by piece, through its excellent detection capacities in the infrared spectrum. Imagine yourself in an art gallery, perusing vast works captured by the James Webb Space Telescope. These images are amazing, with distant galaxies sparkling on the enormous canvas. Among astronomers and cosmologists, there is a sense of awe. The typical statement heard is that this is absolutely unforeseen and has shaken the foundations of their understanding of the universe. Despite the fact that official reports have not revealed much about it, the genuine test lies in a newly accepted hypothesis, the Big Bang Theory. The assumption being called into question is the possibility that our universe started through a gigantic blast some 13.8 billion years ago and has been expanding like a giant balloon ever since. This theory has been key to our understanding of cosmology for many years. However, groundbreaking observations made by the James Webb Space Telescope have cast doubt on its validity, creating a ruckus in the scientific community. We can almost imagine Alison Kirkpatrick, an astronomer at the University of Kansas, questioning her entire career as she lies in bed. Why so much shock? The justification for this bewilderment lies in the fact that galaxies captured by the James Webb don't behave according to what the Big Bang Theory would predict. They are too small, too uniform, and seem to be of an age incompatible with this hypothesis. Moreover, their numbers are surprisingly high. To rearrange these errors, we imagine the universe as an expanding globe. According to conventional theory, galaxies shouldn't appear smaller as they move away from us. At one point, they ought to start to appear larger since their light would have had to travel from when they were closer. This rare yet significant change in the conceptions of an expanding universe is evident in the James Webb images, where galaxies seem to maintain a similar size to those closer to us. Truly, the conventional theory might make some mistakes. Astonishing as it may seem, recent research has shown that the Big Bang Theory is wrong in 16 of its predictions, which is a significant number. The only prediction that is accurately verified concerns the abundance of deuterium, a type of hydrogen, but that is just the beginning. The theory we have long relied on has also been predicting twice the amount of helium and 5 times the amount of lithium that we actually find in the universe. In addition, the Big Bang Theory faces challenges in explaining the large structure observed in the universe. According to this hypothesis, these structures are simply too large to have formed in the time since the beginning of the universe. Also, the theory has difficulties in predicting the density of matter in the universe. And here comes an interesting surprise. Those supposed imbalances that were thought not to exist in the cosmic microwave background actually turn out to be real. This adds an unexpected twist to the cosmic narrative. This leads us to the James Webb Space Telescope, an amazing technological achievement that may hold the answers to these enormous scientific inconsistencies. These errors may seem like minor details in the vast scene of cosmic data we have gathered, but it is important to note that they are far from insignificant. Every little mistake adds up to a missing piece of our cosmic puzzle, preventing the formation of a complete picture of the nature of the universe. These irregularities raise critical questions about everything we assumed we knew about the origin and evolution of the universe. They challenge our understanding of cosmic structures and the very fabric of space-time, which fundamentally affects our comprehension of universal expansion, gravitational waves, dark matter, and even the ultimate fate of the universe. For example, if the density of matter turns out to be variable, this would alter our conception of how galaxies are formed and developed, as well as our approach to the role of dark matter in this entire process. Similarly, unexpected disparities in the cosmic microwave background could affect our understanding of the initial conditions of the universe and its evolution. These irregularities even have implications for our very understanding of time, as they are closely linked to the evolution of the universe since the Big Bang. If we conclude that the Big Bang theory is not entirely accurate, we would be faced with the need to rethink our perception of time, its flow, and its relationship to space. Discoveries of this nature could trigger a paradigm shift in our understanding of space-time, similar to what happened when Einstein introduced his theory of relativity. We would be on the edge of a new understanding of the universe, in which it would be necessary to recalibrate our cosmic clocks and redefine our coordinates in the universe. Clearly, the universe holds a few surprises in its chest, wouldn't you say? Have you ever puzzled over whether time, as we consider it, is a substantial reality or simply a human construct that we use to distinguish the past from the present? It is a very complex question, but we invite you to join us in its exploration. There's a theory that time could be an illusion generated by our human memories. According to this hypothesis, everything that has happened or will happen is happening right now. It is a truly astounding concept, isn't it? If we dig deeper into this idea, we tend to think of time as something that flows perpetually forward. However, here's the intriguing thing. The laws of physics do not require that time works differently if it moves forward or backward. The Big Crunch hypothesis, for example, proposes that when the universe stops its expansion and begins to contract, time could go in reverse. As the universe contracts, the temperature will increase, like a Big Bang in reverse. Now, what happens after the Big Crunch is a question that has puzzled many of us. Some theories raise the possibility that another universe could emerge from another Big Bang, while others suggest that our universe could restart at another point as if there were a cosmic bubble. There are even theories that the cycle could repeat itself over and over again, resulting in countless universes. The intriguing idea that time could be bidirectional, that is, that it can flow both forward and backward, has led some scientists to the bold conclusion that time, as we perceive it, is actually a construct created by humans. They argue that we live in an interconnected space-time, an idea that finds support in Einstein's theory of relativity. Under this premise, all past, present, and future events occupy their respective coordinates in space-time, which unfolds in 4 dimensions. So, what does this suggest for us? Essentially, it suggests that everything has a reality as solid as the present moment and that the past and the future exist somehow, somewhere in space-time. MIT physicist Max Tegmark expressed this idea persuasively by describing that we see our world as a 3-dimensional space where events happen in time, but in reality, it is a 4-dimensional space where everything just is. If this approach were true, time would be revealed as an illusion. Past, present, and future would coexist continuously. Certainly, these ideas are profound and challenging, but they are fascinating to consider as they show how mystical and mysterious the universe can be. Julian Barber, an English physicist, provides a novel perspective on time in our universe. His argument is based on the concept that reality is comprised of a series of discrete moments, comparable to individual photographs in an album, with each image representing a unique instant. For Barber, our perception of the past is reduced to a construct that relies on the memory stored in our brain, raising the possibility that the concept of the past is largely an illusion. Barber addresses this idea throughout his theories of spacetime, in which every moment exists in a place within a vast landscape that he calls Platonia. In Platonia, each point represents a present, and this scene is governed by precise mathematical rules that make it inherently timeless. This perspective is related to the illustrious name of Albert Einstein, whose theory of spacetime is central to our current understanding of the universe. However, the implications of this theory and our understanding of it have raised significant questions. If Einstein's concept of spacetime were to be proven incorrect at some point in time, would it be necessary to discard it altogether in the pursuit of a more accurate understanding of the universe? As we delve deeper into the mysteries of the universe, one cannot help but marvel at the complexities that unfold before us. The exploration of space-time, a concept integral to our understanding of the universe, continues to intrigue and challenge the scientific community. At its core, space-time unites the three dimensions of space with the dimension of time into a single continuum, a framework originally conceptualized by Albert Einstein's theory of general relativity. Einstein's groundbreaking theory revolutionized our understanding of gravity, positing that massive objects like planets and stars bend the fabric of space-time, creating what we perceive as gravitational attraction. This elegant model has stood the test of time and countless experimental validations, forming the backbone of modern cosmology. Yet, as with any scientific theory, the evolution of knowledge and the emergence of new data inevitably challenge established paradigms. The scientific community remains open to the possibility that future discoveries could necessitate revisions to our understanding of spacetime. If we ever reach a point where Einstein's spacetime is proven incorrect, the response would not be to discard it wholesale but to refine and expand upon it. This iterative process is the hallmark of scientific progress, wherein each new discovery builds upon the foundations laid by previous theories. In the quest for a deeper understanding of the universe, researchers have proposed various extensions and alternatives to Einstein's spacetime framework. Theories such as quantum gravity, string theory, and loop quantum gravity aim to reconcile general relativity with quantum mechanics, addressing the limitations and gaps that arise at the smallest and largest scales of the cosmos. These theoretical advancements, though not yet fully realized, represent the ongoing efforts to refine our understanding of spacetime. At the heart of this exploration lies the recognition that the universe is a complex, dynamic system, far exceeding our current comprehension. Each new discovery, whether it challenges or confirms existing theories, brings us closer to unraveling the intricate tapestry of reality. The journey of scientific inquiry is an ever-evolving process, marked by curiosity, skepticism, and the relentless pursuit of knowledge. As we gaze into the cosmos, we are reminded that our understanding of the universe is a work in progress. The questions we ask today may lead to answers that reshape our perception of reality tomorrow. In this grand adventure, the spirit of exploration and discovery propels us forward, inviting us to embrace the mysteries of spacetime and beyond.